Hello. We are going to continue the review of statistics that we have been doing so far. In the last lecture, we wanted to know about the sampling distribution, and there are four major issues we need to consider. First, what is the mean of the y bar, the sample mean? And second, what is the variance of y bar? And third, does y bar become close to mu, the true mean, when the sample size is large? And finally, four, what is the distribution, what's the shape of the distribution for this estimation error? Y bar minus mu is the estimation error. Then when n is large, what is the shape? That's these four questions are important, and actually the answers in the end are very straightforward and well known. So first, the mean and the variance are given by these. The mean of the sample mean, the expected value of the sample average equals to the population mean of y, what you want to estimate. And the variance of your sample average equals to the population variance of y divided by the sample size. So as n increases, when n goes to infinity, the variance of your estimator will converge to zero, which is nice because zero variance means there is no uncertainty. So your estimator will be more certain and more accurate as n increases. And it's intuitive because the more observations you have, the better you can do. So that's not a surprising result. So combining them after many mathematical steps, but you don't need to know, but just understand the key idea. I want you to understand the key idea. So if you can just take these two results, the mean and the variance, take these forms, then from there you can see that, as I said, as n goes to infinity, the variance goes to zero. So the sample average will have no random errors in the limit. That's the idea of this limit, right? So because the mean does not change, which means in the end there is no randomness, there is no uncertainty, there is no noise, no errors, and that means y bar will be always mu for certainty with 100% in the end, in the limit. So this idea, by the way, this is not mathematically rigorous, but still, roughly speaking, it's not wrong. So I just want you to explain what the mathematical steps wanted to say, and this is kind of a summary of the idea. So, but if you are more serious about mathematical proofs, then contact me. You are very welcome, and I'll be very glad to teach you the mathematical details, which is my major, but I understand you don't like it and it's difficult, and frankly, it's not that useful. Understanding the mathematics behind it will be nice, and but not that useful. Anyhow, so then we say that we define this case as, we call this convergence in probability. So sample mean converges in probability to the population mean. This is the law of large numbers. So as n goes to infinity, as the sample size increases, your sample mean converges in probability to the population mean, and notation goes like this. So converges, there is an arrow, but you have to put p because it means that the object, it means the convergence in probability because the object is random. So you have to denote that this convergence in a distribution sense, probability sense. So you put p there. So we have answered three questions. What is the mean? What is the variance? and what happens if n goes to infinity. And then the fourth question is actually the most difficult and also very important and most useful. That is based on the central limit theorem. So in the end, what we want to do here is the result, simply speaking, the result is this. So the distribution of y bar, the sample average, is well approximated by a normal distribution. So when the sample size is large, enough, then your distribution will be a normal distribution. And the normal distribution is a very well-known, widely studied, widely used, commonly used distribution. Even if, for example, even if your boss does not understand any statistics, but still your boss in the future will understand the importance of the normal distribution. If you say it is a normal distribution, then in most cases should be okay, I believe. So y bar, so because we learned that the mean is mu and the variance is sigma squared over n, so combined with this normal distribution result, you can say that y bar, the sample average, is approximately a normal distribution with those two parameters, right? So the parameters are obtained earlier, and in practice, we do not have this mu and sigma squared. So mu and sigma squared are usually what you don't know. They are from the population, so you cannot calculate them. So in this distribution is normal, but we cannot calculate this. So alternatively, we standardize y bar. So subtract the mean and divide by the standard deviation, and then this standardized form is approximately a standard normal distribution. The standard normal distribution is a special normal distribution with mean 0 and variance 1. So standardized normal distribution is a standardized sample average is a standard normal distribution, which is a very powerful result, because from here you can see that in the numerator, y bar sample average is your estimator, and you are estimating mu of y. So you are estimating mu of y by an estimator y bar. So the difference is the random error, and this is your estimation error. And after standardization, the estimation error is a known distribution. It's a well-known, nice, well-behaved, and easy to handle distribution. So that means you know how big the error is, or how likely you are going to miss the range or so. So this is a very powerful result. But one important assumption here is that the sample size should be large. The larger and the sample size is, the better the approximation is. So as n increases, it's kind of convergence. As n converges to the infinity, then the distribution, the shape of the distribution, converges to a standard normal distribution. That's the result. Graphically, this is what you saw earlier. So think about this. It's like coin toss. You are throwing coins, a certain number of coins, but strangely, it's an unfair coin. The coins are unfair. Suppose that the probability of heads is 78%. Just intentionally, a strange number is chosen to show that this, even if this strange case converges to a normal distribution. So suppose that, think about a coin which has 78% probability of heads and the other 22% tails. Then the mean should be here. Mean is 0.78. And when you throw two coins and calculate the ratio, the percentage of heads out of two results, then you get either 0 or 0.5 or 1. And probabilities can be calculated. right? And when you throw 5 coins, there can be 6 different results. No heads, 1 head, 2 heads, 3 heads, 4 heads, 5 heads. So each represent 0, 0.2, 0.4, and 60%, 80%, 100% heads. And the distribution can be calculated or simulated, and you have this. If you increase the number even more, like 25 and 100, then the possible values, the results can take increases, and the histogram looks more finer, becomes finer, and in the end it becomes smoother and looks like a bell curve. But at the same time, remember, the variance decreases. We have learned that the variance decreases, but the center does not change. The center is always 0.78. 0.78, so center does not change, but the dispersion decreases. So in the end, the graph looks like a big spike, a tall tower at the mean. In the end, there is 100% whole probability will be put on one point without any potential errors. This is the central limit theorem. So the central limit theorem focuses on the shape, which is the normal distribution shape, which is the bell curve. So as you see, if you compare the graph with normal distribution, you expect, then it's this is very close to, very well approximated by a normal distribution. By the way, this graph is after standardization. So when you standardize the sample average, as you can see, the histogram is very well approximated by a normal distribution. Even though there are some small approximation errors, but those errors will disappear as the sample size increases. For example, now this example comes from the case when you throw 100 coins. But for example, when you throw 1 billion coins at the same time, then the result will be almost perfectly normal distribution. So that's mathematical theory, which is very useful and powerful. So normal distribution is maybe the only distribution you need to understand throughout this course, and many distributions will be approximated by a normal distribution or a variant of the normal distribution. So a normal distribution is the most important one. Okay, I'm going to resume this topic in the next video.